Welcome back to the channel. Thank you guys for joining again. Today I'll talk about one of the most important topic in mathematics, especially in calculus. So we'll talk about the fundamental principles of calculus, which is nothing but the differentiation. Okay. So let's talk about the differentiation. So Newton was the first person, or I would say Leibniz, in parallel. They both have uh, talked on differentiation. In fact, they have invented the method to differentiate the functions. Why they have done is that to solve the continuous variable problem. Earlier, we had algebra, geometry, and the arithmetic, and they solved the problems in area of mathematics using the quantitative discrete approach rather than the continuous approach. So for example, Newton had this problem to deal with is that let's say apple is falling right under the gravity. So every second this velocity increases, right? So what if we have to find at time t what has been the velocity, how much it has increased from 0 to certain velocity, right? Because the velocity is increasing with the rate of g. Here it is a constant rate, but let's say if the rate is variable, then how would we find out? So for that purpose, he calculated like we have to find the velocity at t and then t plus delta t and divide them, you'll get the rate. So for example, velocity at t plus delta t would be v, and then minus third at t and divide with the, and if it tends to slow down this time interval, decrease the time interval to the 0, it becomes nothing but the uh, differentiation of the velocity with the respect time. So to understand this in more generic way, I would say, let for example there's one graph, for example, with some variable. If you have to find out the rate of the function at which function is increasing, we have to find out this tan theta, the slope. The slope is nothing but this distance uh, and divided by this distance. So let's say this is x, this is x plus h, this would become fx, this would become fx plus h. So that way we would have this distance would be fx plus h minus f of x upon this would be x plus h minus x, xx would be cancelled out and it become this, and where the h tends to 0. So this becomes the fundamental or the first principle of derivation. Now, let's solve some of the derivatives using this formula, right? So we'll take, for example, let's say we have x cube. We'll solve the derivation of this. How we arrived at those formulas we used in differentiation using first principle. And what happens in first principle, that we assume that there is a one h component which is very near to the x, and what if this is 0? We apply the algebraic operations on the top of that and we'll find out the result and we can use that. So using first principle, we'll write fx plus h minus f of x upon h. I'm not writing the limit h tending to 0 all the time to save the time. Okay, so for example, we'll write x cube this way, then x cube upon h. After expansion, the x cube will be cancelled out and we'll have 3h square x plus 3hx square plus h cube divided by h. H will cancel out this, right? This and this. Wherever the h is there, since h is 0, we can eliminate that 0 and remaining is 3x square. So that way we could write d of dx upon x cube is this much. We can generalize this formula x and there we have to do the binomial expansion, and then we'll get the formula like this. Here n should be greater than or equal to 1. Okay, and then we'll solve for other functions. Let's say if we have to solve for root x, then again I'm not writing the detailed function, but you could write x plus h minus under root x upon h, right? And then we'll expand this. How would we expand this? X plus h upon half minus under root x upon h. We can take the common. Under root x could be the common, and we'll have 1 plus h upon x power half minus under root x upon h. Since h is very small to x, since h tends to 0, we can expand this binomial function like this: 1 plus half h by x, and the remaining part would be 0 and very minimum, so we can ignore that, minus under root x. Now when we'll expand this, under root x will cancel out, and they, by multiplying, would become h upon 2, and then under root x, and then x would be again under root x upon h. H would be cancelled out, and result will come half under root x. So the differentiation of under root x with the first principle would come like this. Let's solve for another function. Let's take sin x. Okay. So through first principle we'll have sin x plus h minus sin x upon h. I'm not writing limit h tending to 0 and fx. I hope you can infer that too. So let's expand this and simplify through algebraic operations. Now this is a sin a plus b formula. So we can apply sin x cos h plus sin h cos x minus sin x upon h. Now we'll put this term together and we'll take the common. Sin x and cos h minus 1 will come in one bracket, and there would be sin h upon cos x. Also we'll take the h with each of one. Now we know sin h upon h, if h tends to 0, it comes around 1. Why? Because if you take sin h, sin theta upon theta, if we take the theta very small, sin theta and tan theta all becomes theta, because what happens when we take this small theta, this perpendicular become the shorter one, very short. So there no sin theta or tan theta will be, there would be no separate identity of tan theta, sin theta, because your perpendicular is almost 0 when theta is 0. So that's why we can write sin theta, tan theta, theta is equal to theta when theta is very small, and then theta would cancel out, it becomes 1. So we can put this result at 1 into cos x, and this when in similar fashion, when theta becomes very small, right, this cos function becomes 1. Why? Because when theta is very small, it will flatten out, like the perpendicular, the base and the hypotenuse would be the same, and in cos theta formula it comes like base upon hypotenuse, and since they would be same, so base upon hypotenuse would be same, so that will come 1, and putting 1 here, 1 minus 1 will become 0, so sin x into 0, so the resultant would come cos x. So we can write d of dx of sin x is equal to cos x. Let's solve for another example. So here it comes. So let's take ex. Okay. So again, with using the same principle, first principle of derivation, we'll put ex plus h minus ex upon h. And we can take ex common here, it will come eh minus 1 upon now now using Taylor series, if you remember, ex expansion comes like 1 plus x upon factorial 1 and plus x square factorial 2, something like this, right? Now ex minus 1, it will come around ex minus 1, we can write h upon factorial 1 plus h square upon factorial 2 and dot dot dot, right? And now if we take h common from here, it would become like 1 plus h upon factorial 2 plus dot 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 upon h, and h would cancel out, and this part would become 0 since h tends to 0, so remaining would come ex. So we can write d of dx, ex is equal to ex. Let's solve another example. Here takes log x, log natural x, again with using same principle would come log ex. I'm not writing e, it's a natural log, so we can write ln x, and with the using log properties, we can write log x plus h upon x upon h, and then we could write it like 1 plus h upon x upon h. So if we divide by x and x, why I'm doing that? Because there's one result with this h tending to 0, or this part tending to 0, it becomes 1, like log 1 plus x upon x, it becomes 1. Why? Again, the Taylor series, log 1 plus x becomes like h plus and x square upon something factorial and then dot dot dot, and again when we divide both sides the x, it will come like 1 plus something, and that 1 plus something would become 0 and it become 1 by x. Another principle we can use is that if we take, we can rewrite this like this way, h upon x log 1 plus h by x. So this comes as like log 1 plus h by x upon power 1 by h by x. So this again become the definition of this 1 plus x upon 1 by x if x tending to 0, right? It becomes the definition of e, and from the property we can take the limit inside the log function and take log outside, because it's property of log. We can write 1 plus h by x and 1 by h by x, and since h by x is tending to 0, it will become e, and then log e becomes 1, and there was x remaining here, right? Let's take x remaining all the time, so it becomes 1 by x. So we can write d by x of log x base e, it becomes 1 by x. So these being some of the fundamental functions. We find out their derivative formula, differentiation formula using first principle derivatives. First principle derivatives are used whenever we use squeeze theorem, roll mean theorem, right? Where you can't really understand the function, it's in continuity or in its differentiability, because they are divided into intervals. So then we take use the first principle to understand their nature in x plus h direction or x minus h direction, like 0 plus or 0 minus interval, and find out their differentiability, right? So for example, some functions like this or mod x, of such nature we use first principle to identify their differentiability, and there are a lot of theorems like roll mean theorem, and there they use the first principle to find out their differentiability and what is their differentiation in particular interval, because first principle is the fundamental way to find out the formula of any function if you don't remember that. Thank you for watching this.